Right, our final presentation is from Wojciech Benesch, who is working with a colleague of Zuzana Boukalova, and is about geophysics, I guess.
Yes, yes. Okay. Thank you, Jonathan. Yes, I agree. Maybe this title is a bit long and a bit complicated, but I try to explain what about it will be. It will be about application of geophysical method for dike inspection in our country, in Czech Republic, when we use GMS methodology. And also, very briefly, I will describe how we developed the database of the geophysical measurement, of this type of measurement. And in the end of the presentation, I will present some, I hope, interesting result from pilot site Humber Estuary in UK. This is the pilot site of Flood Probe project. Very shortly, what it is GMS, geophysical monitoring system. It is methodology which combine fast and effective geophysical method with, we can say, heavy, more difficult method. This fast effective method we use for description of long section of embankments. Heavy method we use for detailed study of some typical or problematic segments. Basic method for this methodology we use also analysis of repeated geophysical measurement, which can help us to see or interpret it possible seepage area. We name this type of anomaly unstable anomaly. I think when you look on the face of this man, it is clear which method is fast and effective and which one is heavy, I hope. Yeah. All the data which are collected for this type of... Okay. Which are measured for this type of survey grow up the database. We use the Daikin system software for growing up, for development of this database. There is the couple type of the softwares. First is Analyzer, which we use for the data processing of EM measurement. There is some new type of information. We define quasi-homogeneous blocks, unstable anomaly, on-base interpretation of repeated measurement, and also we try prepare some function which describe some risk assessment on the embankment together with visual inspection and so on. Very fast, I will skip these pictures. It is the view on the interpretation on the software. There is some analysis of repeated measurement. This is software for administration of localities and for download the data into the database. And maybe important part of the software is viewer, which is for end user, which is working with this type of data. It is based on some map of some GIS software, and you can see like lines here, the measured profiles where the colors show some parameters which is described on this site. For example, this one is some quasi-homogeneous blocks of this part of embankment. This is something more in detail. You can study in detail also the graphs of measured parameters and also some diagnostic or detailed measurement. This is, for example, resistivity cross-section through the embankment. Also, it is possible to connect the photo documentation and reports, etc. Now, at this moment, we can say that this system working on 3 river catchment in the Czech Republic, and approximately 700 kilometers of profiles is covered with this type of measurement. It is about 30% of all embankments. And the database working on 2 river catchments, I hope that in very short time on 3 river catchments also. A few words about future of this system. We would like to hold this database and this system like open system for all type of linear measurement, new method and new equipments. And also we are working together in cooperation with colleague from Trinity House, Dublin University, about inversion of EM measurements. There is some examples what it means. This is the resistivity cross-section from, we can say, classic electric resistivity tomography. You can see here, for example, some strong change of resistivity of materials in near surface zone, and this is the 1D inversion of electromagnetic data, this one, and you can see very nice fit of the information. And what we can say, collection of this data is about, I don't know, 1 minute, something like this. This one needs some hours, maybe 1-2 hours. This is another example for area Hamburg estuary, which is more homogenic. And now I will skip into the Hamburg estuary testing site, because we concentrated on 2 main tasks. One is, we can say, long-term monitoring. We measure our testing site twice time in 2010 and 2012. And also we try to study influence of tide changes on embankments and seepage area. This is the extent of our profile. It is 3 kilometer long section of embankments. Altitude of these embankments is about 3-4 meters. Remember, please, this area where was described some seepages. We can say that on all distant of this section there is approximately 13 places with possible seepage where is moist soil and some typical vegetation. On this picture you can see distribution of apparent resistivity from this fast measurement. There are 2 profiles. Line which is closer to the river is on the X of embankment, and the second line on countryside is on air side, air slope of embankment. You can see here these blue sections on the countryside, and these sections are mostly with some seepages what about I speak before. This is the analysis of repeated measurement. It means that the blue line is measurement from 2010. We selected 1 working frequency. It is sling-gram method, and the red one is measurement after 2 years. The general shifting of the data is dependent of change of the weather condition during the measurement. It is nothing we can say interesting, but we computation from both the curve, some residual anomaly. It is this complicated curve. Here is something more in detail, and we are looking for this significant decreasing of resistivity section in time. This is the result. This red dot is our interpreted area with this shifting of resistivity in time, and when we go to some conclusions, we can say that we selected 23 unstable segments, we can say, and we have described 13 sections with visual indication of some seepages. In the end, all seepages include unstable anomaly. It means that our unstable anomaly cover all these potential risks area. It means that I think that this analysis of repeated measurement really can help with seepage detection. Last example is short-term monitoring. We try to see the effect of tide changes of water level. This is the system of profile in one seepage area. On this picture, you can see some different resistivity cross-section in different position on embankments. And what you can see, this is the river side, this is the air side direction. On the middle, this structure is embankment. You can nicely see the effect of seepage curve through the embankment from one side to the second. And what is very nice visible, that area of seepage show that this end outlet of this seepage curve is much higher in air side slope than the others. Here it is, I hope, a bit more visible. What is this shifting, what I mean. This example is a result of monitoring. There on this side you can see again the couple of cross sections, but this is one position, and the same cross section was measured in time each 2 hours. It means that we measure between high tide to the next high tide event. The change of water level during the high tide and low tide was about 7.5 meters. When you look to the cross sections, you can say there is no change. Therefore, we compute some differential cross sections. It is this set, and you can see here some development of some anomaly which is going on this direction. And what is important, we also select on the air side one point, this one, and here you can see the development changes in time of resistivity at this point. Same situation, but in the area with seepage. Also, you can see this set of the cross-section and residual cross-section, differential cross-section. Maybe on this detail I can try to explain what we interpreted in the end. Here you can see non-seepage area and seepage area. You can see that this pass, this anomaly, we interpreted this anomaly like seepage pass through the embankment or below the embankment. You can see the outlet is directly on the air side. And on this example, it is somewhere 10-20 meters away from them two in some drainage corridor. Okay. Here you can see the change in time, the resistivity. You can see the opposite direction. It is another parameter. It is self-potential parameter which we measure also. And what was big surprise for us, that on seepage zone we can see some measured changes very fast. It means that exists communication during the tide changes, and it means our interpretation, that it is on base some system of cracks which this seepage transport or move on the air slope. This mechanism is more unsafe than simple filtration, and we also try to make some simple drilling, and we really catch some we can say open crack filling with water at this position. Thank you.
Thank you. So I think we're almost out of time, but some very interesting results, and I can say, because I was a little bit involved in this, that we were very concerned about whether the salt would make life really difficult, but
yeah,
it seems as if it's helped because it gives much higher signal, perhaps.
That's right, yeah.
Yes.
That's right.
Okay, well, thank you very much.
Lower noise and better signal.
Yes.
Right.
Okay, well, thank you very much, and I hope you've enjoyed this session, and hope you enjoy your lunch now. I don't think I have any announcements for you, so...